In this video we're going to talk about scientific notation. And scientific notation is a way to write very large or very small numbers. And in this video I'm going to start off just focusing on very large numbers. And if I have time I'll do very small numbers. If not, I'll just make another video with very small numbers. Maybe the first time you encountered scientific notation without even really knowing it is on your calculator. So I pulled up this calculator from just from the internet here, and let's see if we take and you can do this on your calculator with me if you want. 9 8 7 6 5 4 3 2 1, and we take that to the second power. So I hit squared and we get this thing. What the heck is that? 9.754610578 e plus 17? What the heck does that mean? Well, that is scientific notation. This number that we punched in is too big. It has too many digits to fit on this calculator screen. So this is a shortcut or shorthand way to write this very, very large number. So I'm going to write it on my board over here. 9.754610578 e plus 17. And that was 987654321 squared. I would really encourage you to do this on your calculator that you use so you can see what your calculator says. Each calculator is a little bit different. The one we saw said E17. Some calculators might show, instead of the E17, it might show a little 17 up there like that without the E. Some calculators show all these digits, and then instead of the E plus 17, they actually show times 10 to the 17th, which is exactly what E plus 17 means. It means times 10 to the 17th power. So the positive 17 is the exponent, and E is telling you that this is your exponent, and you just have to know that it's 10 to the 17th power. So we have 9.754610578 times 10 to the 17th power. Now why 10 to the 17th power? Why is our base 10? The reason is because when you multiply something by 10, it just moves the decimal one place. Let's digress for a second and think about if I take 25 times 10. That's 250. My decimal in the number 25 is not written, but it's right here. When I multiply by 10, my decimal moves over 1. I have to add a 0, and I end up with 250. If I have 2.5 times 10, my decimal gets moved over one place, and my answer is 25. If I'm changing my shades of green here. If I have 2.5 times 100, I have two zeros in 100, so it's going to move my decimal two places, which would give me 250. So when you multiply by some power of 10, it moves the decimal as many places as there are zeros. 100 is 10 to the second power, 10 squared. So it moves the decimal two places. Whatever that exponent is, it moves the decimal that many places. So if I had, let's pick a different number other than 2.5. If I had 1.73 times 1,000, if you want to punch that into your calculator, you can, but you don't have to, because when you multiply by 1,000, it just moves the decimal the same number of places as there are zeros. Now this only works for powers of 10. It's not going to work if it's 2,000 or 4,000. You'd have to multiply by 2 and then move the decimal three places if you were multiplying by 2,000. But if it's a 10 or 100 or 1,000, you just move the decimal as many places as there are zeros. So in this case, it's going to move it three places. Once around the 7, once around the 3, and then once more, which means I would have to add a 0. So I get 1,730. 1,000 is 10 to the third power. 10 times 10 times 10 is 1,000, or 10 to the third power, which moves the decimal 3 places. Back to our number up here, our big huge number times 10 to the 17th. Well, if I take this number times 10 to the 17th, that means that I would have to take this decimal and move it 17 places to the right to get my actual answer. Well, it's actually going to be an estimate of my answer. Let's go ahead and do that. You know, hey, we got the time. So moving it, the first few times I'm going to move it here is going to be going around these digits, and then I'm going to have to add zeros. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would have this number moving it 9 times, and then I'd have to add zeros for my other places to get to 17. So there'd be 10, 11, 12, 13, 14, 15, 16, 17. And then I could put some commas in there to try to make sense of this number. You're probably asking what number this is. Let's see. This is millions. This is thousands here. These three are thousands, so those are millions. That is 800 million, 57 billion, 461 trillion, 975 quadrillion. So that would give us 975 quadrillion, 461 trillion, 57 billion, 800 million would be the answer. Now, this number is an estimate because the actual number would have digits here. But we don't know what those digits were because our calculator cut it off. And we can only estimate after that and say that it's zeros. So you'd have to get a calculator with more digits on its screen to get the actual answer. The truth is, when you get to this large of numbers, there's a lot of estimating that goes on because being able to measure them is difficult. For example, you know, how many miles is it to the sun? Let's go ahead and see what we come up with. So this website is telling us how far is the Earth from the sun. 93 million miles, approximately 93 million miles. It's not exact. I mean, 93 million, it's not going to be exactly 93 million. When we're measuring something that far, we end up estimating. Let's look at that number, 93 million. Let's get rid of this business here. How far we are from the sun. And let's talk about how we would write that number in scientific notation. 93 million miles. So that's the distance from the Earth to the sun. So to write a number in scientific notation, we need to know the general form of scientific notation. Scientific notation, you're always going to have some number here times 10, and then you're going to have a power here. So that's the general form. You need to figure out what number goes in this underline and what number goes in the box for the exponent. The number that goes on the line here has to meet a certain criteria. It has to be bigger than or equal to 1. X is going to represent the number in this line, and it has to be less than 10. So it could be 1 or bigger, but it has to be less than 10. So basically what that means is it's going to be a one digit and then the decimal. I'll show you an example. That's a little hard to explain with these symbols, but you'll get it when we do an example. And then you need to figure out the exponent. Remember, the exponent is how many places the decimal is going to move. So if we came up here to this 93 million, and right now our decimal is right here at the end, and we're going to move this decimal back to the left until we get a number that meets this criteria right here. It has to be bigger than 1 and less than 10. So if I move it, I'm going to have to move the decimal all the way over to here to get 9.3, which is between 1 and 10. I'm going to explain in a minute here why this equal to thing is here. Let's not worry about that right now. Basically just think between 1 and 10. So I got to move this decimal all the way over here until it's 9.3. Now, how many places did I move the decimal? Well, let's count. 1, 2, 3, 4, 5, 6, 7. That's my number that goes for my exponent. So I have 9.3 times 10 to the 7th. And that would be 93 million in scientific notation. Let's look at another example where maybe I can explain the deal with this 1. Let's say I have the number, let's go just 1 with a whole bunch of zeros here. 1 with 9 zeros, alright? So that's 1 billion. If I want to write 1 billion in scientific notation, I'm going to move my decimal again until I get a number all between 1 and 10, but it could be equal to 1. And in this case, it is going to be equal to 1. So I'm going to move it all the way over to here. Boom, right there. So I have basically 1 digit to the left of the decimal. So notice this number on the line can be 1. In this case, it would be 1 times 10 to however many places I had to move the decimal from the end to here, which is 9 places. So in other words, it's going to be 1 times 10 to the 9th power. That's why I have this equal to part here. What's on this line could be equal to 1, but it's not ever going to be 10. It's always going to be less than 10, like this example up here, 9.3. See, if I put the decimal over here, it would be 10, but I'm not going to put it there. I'm going to move it over there and make it 1. I hope that makes sense. I mean, most of the time you can just say between 1 and 10, but it could equal 1, but it's never going to equal 10. It's always going to be less than 10. Some number between 1 and 10 or equal to 1. Alright, let's look at another example, and maybe you could try this one. You could pause the video and see if you could write this in scientific notation. 6, 5, 0, 0, 0. How about that one? Okay. Pause it, see if you can write it in scientific notation, and then start it again when you have your answer. Okay, so you know your decimals at the end here, and you want to move it until you get a number that's between 1 and 10, which is going to be right here. That's where you're going to want to move it. Another way to think about it is you're going to have one non-zero digit to the left of the decimal. In this case, your 6. Alright, so how many places did we have to move it to get it over there? 1, 2, 3, 4, 5, 6, 7. 7 again. So that will be your exponent. Scientific notation will be 6.5364. That's with my decimal here, times 10 to the, how many places did I move it? 7. So these two numbers are equivalent. This is a shorthand way to write this number. It doesn't seem really shorthand right now, but if it was, more zeros, it would definitely be more shorthand. Alright, let's try one more where I give you the number in scientific notation and then you write it out the long way, which would be called standard form. Okay, so here's a number in scientific notation. 3.25 times 10 to the 8th power. So pause the video, write that out the long way, the long number. Maybe even think about what that number is, how to say it. Okay, so let's see how you did. Basically, this 8 is telling us we got to move this decimal 8 places to the right. So I'm going to move the decimal 8 places that way. Well, it's going to take 2 places to get around the 2 and the 5. That means the other 6 places are going to have to be zeros. So 3, 2, 5, and then I'm going to need 6 zeros. So it's really important to understand this 8 does not tell you how many zeros there are. It tells you how many places to move the decimal. So if I got to move this decimal 2 places around the 2 and the 5, that leaves me 6 more places to move it, and that's how many zeros I would have. If I put my commas in, I can see this number is 325 million. So that's scientific notation, and it can be also used to represent very, very small numbers, which I will go over in the next video.